Hey folks, so welcome to another lesson on internal resistance. This time we're going to look at how to determine the internal resistance from a graph, and this ties in with Thursday's lesson, which will be doing an experiment to work out the internal resistance of a cell. Now, obviously, you can't do this at home, but you're going to use a simulation on PhET. The video for that is actually already on YouTube, so if you're really keen, you can have a look at that already. When we get back into class, I'm hoping you'll get a chance to do this experiment because this is one of the experiments that I would like you to choose for your assignment. And it's a really easy experiment, takes you 5 minutes to do. The analysis, once you've seen it, is actually fairly straightforward as well. So this is a really, really important lesson. It's also the final lesson in our whole topic about internal resistance. Okay, so today's lesson objectives is determine the internal resistance of a cell from graphical data. We'll do the experimental lesson on Thursday. So a wee starter to get you thinking about this. In maths, how would you describe this line, right? So pause the video and see if you can write down something that describes this line here. Okay, it's a straight line, I'll give you that. I'm not looking for it's a directly proportional or a linear line, a linear relationship, sorry. I'm looking for something else, and that's probably enough of a clue to help you there. So did you get that from maths? The equation of a straight line is y is equal to mx plus c, right? And if you don't, hopefully you recognize this because I'm sure you've all done this in Nat 5 maths. Now you probably also know how to calculate the gradient of the straight line, which is given by m is equal to y2 minus y1 all over x2 minus x1. Okay, and you may know variations of this. So, for example, you might know this equation as yb minus ya over xb minus xa. Doesn't really matter which one you use as long as it's the correct equation mathematically. Okay, so that's the equation for the gradient. You might also know that c stands for the y-intercept, which is where the line cuts the y-axis. So that's the y-intercept. We're going to be using these concepts later on, as you'll see. Okay, and y and x correspond to your y-axis and your x-axis. Okay, so that's the basic knowledge I expect you to have as we go into this topic here. Right, so let's look at this a bit more in terms of the physics now. Okay, so the equation of a straight line is y equal to mx plus c. The equation for internal resistance is E is equal to VTBT plus IR. And these equations are the same mathematically. Now, it might not look that, but if I rewrite this equation to the following, E is equal to IR plus VTPD. Okay, can you see how these equations are now really the same thing, but they've just got different symbols on them? You've got something by itself on the y on the left-hand side, if you like. You've got something that is multiplied by something else, which is like the mx. And then you've got something by itself, which is the y-intercept. Okay? So if you were a mathematician and you were looking at these two equations, you would actually say they actually both describe a straight line. Okay? So what this means is that if you plot the results of an internal resistance experiment, which would obey this equation, because that's what the physics is all about, then you would get a straight line. Okay? Now, when we come to analyze this equation, it's not as straightforward as matching them up as I've done like this. There is a wee bit of a trick to this, which I'm going to show you later on. So just be aware, although I've said these two are exactly the same, mathematically that's correct, but there is still a little bit of work we need to do to actually get them to work in terms of the physics. And this is where physics and maths kind of separate out a little bit. So just be aware of that, folks. Okay, so we're really trying to push this visible learning stuff. So I've made up a new logo for MTV. So hopefully you can understand this one because it's a TV with M inside it. So MTV. And every time you see the symbol, folks, it means think about what it is that you're doing, how you're doing it, and see if you could summarize it on that table that I gave you last time. So what you're going to do today, you're going to add to that table later on, right? And what we're going to do is I'm going to save these and print them off, and then that way you've got these as a copy to help you with your revision, okay? So to do this topic for your MTV, your visible thinking, you need to understand the concepts of EMF, VTPD, and internal resistance. Hopefully you've got a fairly good understanding of what these concepts are. So for example, if you look on your table, you'll see you've got 2 to 5 details about EMF. Those are the things that I mean when I say you understand the concepts. Be able to apply your circuit rules. Again, if you look at your table of ideas, then you know what those circuit rules are. Be able to calculate the gradient of a graph. Now, I've just been through this with you just now, so you may want to add this on to your physical learning sheet when you come to do this, right? So if you're stuck for ideas, look for the slide that has an MTV symbol. They will generally give you an idea of what it is you should be putting down. I don't want to tell you what it is to put down because then that defeats the purpose of the exercise. The whole point of physical learning is that you reflect and think about what it is that you've learned to do, so you can then therefore say, am I doing it well? Am I doing it okay? Or do I need more help? Okay? So let's get back to the physics now. Now, the graph for internal resistance will actually look like this. Okay? So it's not going through the origin, it actually starts at the y-axis and then goes down towards the x-axis. You'll see why in a little bit later on. Okay? So if we look at this, folks, we can see it's not going to be a straightforward, let's just write the equation one under each other and match them up like this. Right? You can't do that. You'll get the wrong physics in this case. So the question then becomes, how do we match the two equations so the physics and maths is actually correct? Okay, now before I move on, there's one wee bit where the maths can help us. Is question for you: if the graph has this kind of slope, what can you say about its gradient? Okay, pause the video, have a wee think, and then I'll tell you the answer. All right, hopefully you got the answer is that the gradient here must be negative. Right? It's negative. It's a negative gradient, right? So that means in our equation here, we should expect to get a minus somewhere in here. So that suggests to you we're probably going to have to rearrange this equation in some way. So let's see how we do that in the next slide. Okay, so how do we match the data from the graph to our equation for internal resistance? That's where the physics takes place. So here's my top tip for you folks, okay? Look at the axes to determine which quantity is y and which quantity is x. So here's my two equations here. Now if I look at the axis, this is your x-axis, and that tells me straight away that I must be x. So there, I can link the two together. So I must be equivalent to x. Okay, so I is equivalent to x. Now, if that's the case, that means straight away I know the gradient must be equivalent to the internal resistance. Right, now notice I'm saying equivalent, and you'll see why later on. Okay, that's a really important point. I'm saying equivalent because that's a slightly different meaning than saying the same as, and we'll talk about that a bit later on. So there's lots of wee subtle points here I want you to pick up. So think about those 2 to 5 details you're going to be writing down about graphical analysis for internal resistance. Now, the trickiest part, or what looks like the trickiest part, is which one of these matches with Y. Because if you think about it, EMF and VTPD both have the same units. So how do we match them up? Okay, well, the tip still works. We'll look at the Y-axis, and we see the Y-axis is a potential difference, a voltage. Okay, so how do we match that up? Well, the one thing to remember about the Y-axis is, what can you say about the voltage along the X-axis? Okay, have a wee pause the video and think about the answer. What can we say about the voltage along the Y-axis? And the answer is, the voltage is changing. Okay, it can either increase, or if you look at the graph, the line of the graph, the voltage, the potential difference, is actually decreasing, isn't it? Okay, it's decreasing. So if it's decreasing, that tells us it must be matching with VTPD. Because remember, EMF doesn't change. EMF is the supply voltage from your cell. It's a fixed number. VTPD, however, can change, because if you draw more current, remember, the VTPD will decrease because your loss volts, the voltage across your internal resistance, has increased. So notice how you can figure out these things. Okay, you can figure out these things. So that's how we match up the equation for internal resistance with the equation for a straight line. Now, okay, so have a go of that yourself on this slide. Write it out, draw the graph, write down the two equations, go through that same process of what matches M and C. Okay, have a go of it, pause the video just now and have a go of it. Right, hopefully you've done that and you found it's fairly straightforward. I'm not going to take you through it again. You can always play the previous slide again if you want. The key thing here I want to talk about now is, first of all, why is the gradient of this line negative, right? And how does that match up with our equation for internal resistance? Well, if you matched up the equation like we did before, and if you rewrote it in the same format, okay, you would actually get this equation here, right? VTPD matches with Y, E matches with the Y-intercept, and IR matches with MX. Now, I've written it in a form where it's E minus IR, but I could, of course, also write it as minus IR plus C. Okay, that's perfectly fine as well, but I thought if I write it that way, it looks a bit neater. Now, if we analyse this graph a wee bit more, this equation a bit more, we can see that the EMF is still the y-intercept. So what that means is, if I know the y-intercept, I can work out the EMF. If I look at this, R is the actual gradient bit, because remember, I matches with the x-axis. Okay, so really, I could even write this equation as minus R I plus E. Okay, and if I look at that, I have a minus R, which means the gradient is negative, and that's why the line slopes this way. And this is really cool, guys, because suddenly, can you see how all your maths and physics is tying together? And can you see how, if you really understand your maths and your physics, you can actually figure out whether or not what you've done is correct? Because if you can't do this kind of analysis, then you know you've done something wrong. Okay? So there's a wee bit of physical thinking there for you, is being able to match up your y equal to mx plus c with your internal resistance equation, and then finally explaining it and making sure it fits the actual data. Okay? Now, a very, very important point, and this is one point I really, really want you to pay attention for with your MTV, is this. Okay? Right? Now, it's very tempting to write minus R is equal to M. Okay? Right? It's very tempting to write that. Now, if you do write that, mathematically, it's not even correct because you've got a negative and then something that's positive. How can something that's negative equal to something that's positive? That doesn't make sense, right? If you wrote this down in your physics, that would be wrong physics and you'll get 0 marks, right? The way I want to write this is I would write down M implies negative R. Okay, in fact, I wouldn't even put the negative there, I would just put down R. So the gradient implies R. Okay, and notice that's a very important point because we're not saying they're equal to each other because that doesn't really make sense because we know physically, that the internal resistance can never be negative. Negative resistance has no meaning in physics as far as we know, right? So that's why you can't say the gradient is equal to R. If you do that, that's wrong physics. You've got to say that the gradient implies R is equal to whatever value you calculate. So just be aware of that, folks, because that's one bit where a lot of people lose marks in. So that's a wee bit of exam technique for you. Okay, so having been through that theory, as always, let's just apply it and see how it works in practice. So this is your MTV. Think about your physical learning here, folks. So this is a past paper question from 2015. Technician sets up the following circuit with different car battery connected to a variable resistor R. So notice you've got your internal resistance. As soon as you see this symbol here, you know you're talking about internal resistance. So you should automatically be thinking this equation here. Okay, so thinking routines, folks, you're thinking straight away KFC. Okay, you've got your load resistor there, you've got your ammeter and your voltmeter. It looks like a standard kind of internal resistance question. So here's the next bit. It says, readings of the current and terminal potential difference V from the circuit are used to produce the following graph. Use the information from the graph to determine the EMF of the battery and the internal resistance of the battery. And notice the EMF of the battery, the first question is only worth 1 mark. So remember, for 1 mark, that usually means a definition or just doing something without having to do a calculation. And the 3 marker at the end suggests you have to calculate something. Notice as well, this is your MTV, so try and think about what it is that you are doing, how you're doing it, and how you would write this down in your summary activity for MTV. Okay, so what do we know about this graph and internal resistance? Well, first of all, we know the following. It's a straight line graph, so it's described by this equation y equal to mx plus c. Okay. We know it's talking about internal resistance because it even mentions terminal potential difference, EMF and internal resistance. So we know we've got to use this equation here. How do we get the EMF of the battery? Well, the first thing we need to do is work out how this line graph relates to this equation here. So remember my top tip, look at your y and your x-axis. So here, my x-axis tells me that I matches with x, so that means these two match together. The y-axis tells me it's measuring potential difference. And again, if you think about it, VTPD can change, but EMF can't. So that means VTPD must match with Y, and that means E must match with C. And that's our answer there. To get the EMF of the battery, we just read off where the y-intercept is. So what I would do, now I can't do this on my screen, is I would take my ruler and just extend that line to where it crosses the x-axis, the y-axis, sorry. And you can see I've done a pretty rubbish job of that, but if you do it properly, if you had your piece of paper in front of you, you could do this properly, and I reckon roughly the y-intercept would be about, well, that's 12, so that's 2, 4, 6, 7, so say 12.7 volts. Okay, there is a little leeway in the exam. If you don't get exactly 12.7 or what they recommend, you can get plus or minus half a box out. You're allowed a little leeway. So don't worry if you don't get the exact same answer as the exam board question. Okay, so 12.7 volts, that's the EMF. And notice how no calculation, I just read it from the graph. That's why it's 1 mark. Okay, nice and straightforward if you can understand how to match these two equations together. The internal resistance of the battery, well, I know from here that I is x-axis, so internal resistance must be given by the gradient. So the gradient, remember, is m2 minus y2 minus, so that should be y2 minus y1 over x2 minus x1. Okay, so we know that that's the gradient there. Now, again, a wee bit of technique for you, and this will come in handy for your assignments. Whenever you're asked to work out the gradient of a graph, you always try and pick 2 points that are far apart. So preferably say at this end here and say this end here. You never pick a point that you plotted, so you would never pick these points that are on the graph already. And that's how you would do your gradient. Now, obviously, you can try and pick points that are easy to read. There's no reason to make this more harder than it is. So again, you might want to pick, say, this point here, okay, and say maybe sort of, I guess it's kind of trickier here, but maybe this point here because it seems like it's halfway, right? Again, there is a little leeway if you don't get the exact same answer. I'm sure you can all do this, so I'm not going to go through the answer completely, but I'm going to show you how I would do it. What I would do is I would pick my 2 points, write them down here. So I'm just going to make up some values, say 1 and 2, and 2 and 3. And then I think it's just good practice, KFC again, making your thinking visible. Write down which one is x1, y1, underneath like this, x2, y2, and then it's just a case of subbing in numbers and number crunching. So for me, the visible learning is this bit here, but it's also to make it easier for you so you don't make any mistakes, right? Now I've spent a lot of time on this slide here because this really is your NTV, the crux of this lesson here. So make sure you understand the concepts I've talked through here. If you need to, play it again. Now, when you get to the final answer, folks, before I move on, you'll get something like this. Again, for argument's sake, let's say you get M is equal to minus 3 ohms, or 3. Okay? Now, how would you write the final answer? I would just write the following. This implies that R is equal to 3 ohms. So that's how I would write your final answer. Don't do anything fancy and try and say M is equal to R or equal to minus R. Just write implies R is equal to 3 ohms. You've got your sign there, your symbol, sorry, your units, and you've got your value, it's positive. That's all you need to do. Okay? Don't try and be fancy, because if you try and be fancy, you can cost yourself some marks. Okay? So finally, as always, practice will make you perfect. So textbook chapter 3.23, there is more information there for you to read up. There's also a wee bit of information about the experiment you're going to do. We're going to do it slightly differently because there's a kit we can use. Have a go at exercise 3.23, and then there's also the questions from the tutorials, questions 13 to 17. Now, I know a lot of these questions will ask you to plot a graph. Preferably, if you've got graph paper at home, plot them on graph paper. If you don't and you've got a printer, you can always Google graph paper and print it off from the internet, right? If you're unable to do this, check my YouTube video because there's an Excel video, a video showing you how to use Excel to plot these graphs. I would like to do this if you can't do the graph on paper, and this will let you analyze the graph to find the y-intercept EMF and the gradient for the internal resistance. Okay, I want you to do either one of these. Either do it on paper or do it on Excel. I'll tell you now, if you do it on Excel, if you can get good at it, it will literally take you 3 minutes. Right? In fact, my video only takes about 1 minute 45 seconds. So if you want to save yourself a bit of time, make sure you check out the video. I'll post this on the message board as well. And then that way you can do your analysis, folks. And that's it.